Hi everyone, and welcome back to another AP Calculus video. Here we're going to talk about parametric equations, specifically polar equations that are represented as parametric equations. And the one goal of this video is to get you comfortable with finding the derivative of a parametric or of polar equations. We're going to learn how to define them parametrically, and basically what we've learned about parametric functions is going to apply here across the board. We're also going to take that derivative and learn how to write the equation of a tangent line to a polar curve. So let's take a look. We talked about in the first video that a polar curve, r equals some function of theta, can be defined as two parametric equations. We have these conversions, x equals r cosine theta and x equals r sine theta. So oftentimes we'll have some sort of a polar function. It'll look something like this, r equals like 3 sine theta, or something like that. It'll involve an angle and an r. And we're also going to remember that when we graph on a polar coordinate system, theta means we're going to rotate around a certain amount, and then r is the length that we travel from the origin to the point in space. So we've got an r, we've got a theta, and we're sweeping around, we're traveling out and around. And creating these cool functions, we're creating things that look like cardioids, lemniscates, roses, things like that. And we'll talk a little bit more about what those graphs look like in the future videos. But if we think of a polar curve simply as a set of parametric equations, having an equation r cosine theta, r sine theta as our parametric equations, we already know how to deal with them. So for example, dy dx would simply be dy d theta divided by dx d theta. In the same way that we have t, theta is our parameter. So we're going to treat them just like we would any sort of parametric equation. So let's use that and let's apply it here to this example. Suppose we have this curve r equals 2 sine 3 theta. And we want to find the slope of this curve. Now this will create a rose. And what a rose is when you graph it, it has a certain number of petals and it kind of looks like a flower. Let's take a look and see exactly what it looks like. So again, if I'm going to graph something on my calculator, I need to make sure it's in polar mode. So I'm going to go to my mode and I'm going to arrow down to right below, make sure it's in radian mode, and I'm going to make sure that polar is highlighted. And if it's not, I'll just highlight it and hit enter. And then when I go to my y equals screen, I can clear out whatever's already there and enter my equation. So 2 sine 3 theta. I'm going to start out with my standard viewing window, and then I'm going to eventually have to zoom in. So you can see this is a rose, it's got 3 petals. So when I zoom in, I'm going to change my x-min and my y-min. We'll go like, we'll go negative, actually we'll go -3 to 3. We'll zoom way in. It was pretty tiny. We can always adjust later on, and we're going to square it up too to get a better picture. But here it is, and then once I have it in my frame, then I do zoom 5 and that squares it up for me. So this is my rose, this is what it looks like. And where theta is pi over 6 is kind of, that's 30 degrees. So that's somewhere like right in over here on my graph. That's what I'm looking for. So it'd probably be a positive slope, so that's kind of what I expect based on how the curve is looking. So let's find out. Let's see what we can do. Now remember, in order to write the equation of a line, we need a point in space, and we also need a slope. So the slope of my tangent line, which is what I want, is dy dx. So anytime you're asked for the slope, it's dy dx. So I need to express this equation as a set of parametric equations so that I can find dy dx. So remember, x equals r cosine theta and y equals r sine theta. R is the equation, so this is where we have to be really careful. So I'm going to put it in parentheses, 2 sine 3 theta times cosine theta. That's my x equation, x of theta. And then same thing here, 2 sine 3 theta, and then you're going to multiply with lots of parentheses, sine theta. So r is the equation when we're doing these parametrics. So this is my y of theta. So to find dy dx, I need to find the derivatives of each of these equations. So I'm going to evaluate those derivatives at at the value pi over 6. Now you could do the product rule here and it would be really obnoxious. You could also just do math 8. So let's review that a little bit. And I'm going to find dx d theta at theta equals pi over 6. So this is how I'm going to show my work on my AP exam. This is the notation that I want to include. And I'm simply going to use math 8. So let's review. So here we go. I'm in polar mode, but it's probably okay. It doesn't really matter. Math 8. There we go. And I'm just going to hit my variable. Now, since I'm in polar mode, it puts a theta in. You do not need to be in polar mode. I'll show you. You can be in function mode and still evaluate. You would just type in x's instead of thetas in the same way that when we do volume or something like that and we have a dy set up, we use the letter x. It's not a big deal. So we're in polar mode. We'll keep it in polar mode. But I'll go ahead and do math 8. I'm doing the derivative of this whole thing. So 2 times the sine of 3 theta. Close the parentheses. Let's do another parenthesis. And then we'll type in the cosine theta. There we go. And then theta equals pi over 6. And we're going to get this value. It's actually going to be square root of 3. Oh, it should be square root of 3. Oh, no, that's -1. Sorry, I was looking at the wrong results here. I have my answers already kind of written out. -1. So remember, your calculator will evaluate it, and something like this is just kind of, oops, there we go. You should get rid of that there. There we go. So again, math 8, I typed in the equation, theta equals pi over 6. And like I was saying, it has theta in there, just like the x. It doesn't need to be a theta, though. You can do this in function mode. But when we get a result like this, we're going to round it to -1. We're going to treat that as an answer like -1. Now, I'm going to go second entry, and the dy is exactly the same, except I'm going to hover over cosine. I'm just going to change it to sine. So if I do a really good job entering it one time through, I don't need to do any of this. And this value is actually the square root of 3. So as I'm kind of looking over this, you know, having this value here, that's fine. But square root of 3 over -1. And I just happen to know that it's the square root of 3. I happen to know that decimal. But if you don't, that's okay. You can still treat it like it's a value. So you get dy, so this is -1, dy d theta, when theta was pi over 6, is square root of 3, or that decimal 1.732, and I'm not at the end, so I'm going to go 6 places, 042, I'm going to go more than that, 0.42725. I'm going to go as many as I can. I know it's square root of 3, so I'm just going to leave it like that. And then dy dx is going to be dy d theta, square root of 3 over -1, so negative square root of 3, or -1.732. Now this was probably a poor example. I don't know that you would have examples on your AP exam where your calculator would spit something out that you'd have to know you need to interpret that as a -1. So this is just kind of one of those situations where that happens. The AP exam, it'll be very clear, and there won't be those types of hindrances where technology can get in the way. If you know what you're doing, you'll be able to find everything just fine. So dy dx is this negative square root of 3. Now, if I want to write the equation of the tangent line, now I need, I've got my slope, now I need my point. So my point here is going to be the xy point when r is, let's see, when theta is pi over 6. So when theta is pi over 6, x will be, I'm just literally going to plug in theta for, I'm going to plug in pi over 6. So x is going to be 2 times the sine of 3 times pi over 6 times cosine of pi over 6. So what? That's going to be 2. That's going to be pi over 2. Sine of pi over 2 is 1. Cosine of pi over 6, that's 30 degrees. So the cosine is the longer side, square root of 3 over 2. So it's just square root of 3. The y is going to be 2 times the sine of 3 times pi over 6 times the sine of pi over 6. So it's going to be 2 times 1/1/2, or just 1. So the point I'm going to use is the square root of 3, 1. So there's my point. I've got my slope. Now I'm going to write my equation. So remember, we use this y minus y1 equals m times x minus x1. Well, we found our y1 was 1. So y minus 1 equals, our slope was negative square root of 3, and then x minus the square root of 3. So there's my equation. And if you had the decimal equivalent, you would be just fine, especially if it's a calculator active exam. And that's fine. But I knew the exact values, so I like to use them that way. But this is the application. This is how we're going to use polar equations to find slopes and write equations of tangent lines. So the key here, just to kind of sum this up, is that dy dx, you have to rewrite the equation, the r sine theta, or the r equals that function of theta. You have to rewrite it as parametric equations. And when we do, another way to think of this, and this might actually be a better way if you want to add this in, remember r is your function. So the parametric equations really can be thought of like this. It's some function of theta times cosine theta, and it's the same function of theta times sine theta. So when we do our parametrically defined equations, it's not just r cosine theta, it's whatever the equation that you're given is. So just like we went down here and we put 2 sine 3 theta in, that's my f of theta, right? So this is my f of theta, this is f of theta, f of theta. So this is how we create parametric equations. And once we start thinking of them as parametric equations, really it's the same process. It's dy dt over dx dt, except now we're using theta instead of t. So the more that you practice with this, and the more that you, try these problems out and practice finding the derivatives and review writing those equations of those tangent lines, the better you're going to get at these problems. Keep practicing. You can do it. You've got this.